Hello and welcome back to another session of Science 122, Introduction to Physical Science. In our last session, we talked about the quantum mechanical model in which we looked at the way that the atom is put together in terms of how we arrange the electrons around the nucleus. Today, we're going to go ahead and take a look at what happens when we use the atoms and that makes up all of matter and arrange them in some sort of logical order. Before we do that, however, let's take a look at a flashback of what we did last time. So in our flashback, we talked about the dual nature of light, that led to the Bohr's model of the hydrogen atom. And then in further advancing it, we looked at something called the matter waves, in which we have now the other duality of matter becoming like wave. And then that led to the wave mechanics and ultimately to the quantum mechanical model of the atom itself. And then you were left with the following think tank question. You were asked, some heavy metal atoms actually emit X-ray photons in their spectra. So the question then is, would this be the result of electrons transitioning between energy levels close to the nucleus or energy levels far away from the nucleus? And you want to kind of explain why. So basically what you want to do is we're going to look at a response from one of our viewers. So let's see who wrote in this time. So it looks like we have a response here. And so let's see who it is that is writing in this time. This is from our viewer Kenny from Kaneohe. And Kenny says that yes, because of the fact that what we observe, is actually due to the transition between different energy levels. In order for you to get high energy like X-rays being emitted, you have to have a pretty big gap between your orbit, so to speak, in the Bohr atom. So in this case, basically the transition has to be from a very, very high outer energy level, dropping all the way down to an energy level that's very close to the nucleus. So from one of the high n values down to maybe n is equal to 1. So with that big jump, you can basically then bring out a large energy photon like that of an X-ray. So basically it's kind of a trick question. You have to kind of transition between both high and low. All right, so with that, let's go ahead and take a look at today's objective in terms of what we want to do. So for today's objectives, basically what we're going to do is start off with building an atom, what makes up matter. So in there, how do we get started making the building blocks of matter? We're going to look at the periodic table, which is a way for us to organize that information. We're then going to look at some general classifications on the periodic table, looking at things that are called periods on the table as well as groups on the table. And so with that, this now leads us to our first topic of discussion for the day. So let's take a look at the first topic. So in this first topic, we're going to look at atoms of matter. How do we go about building these different atoms? So what we want to do is we're going to go ahead and take a look at how it is that we can start putting atoms together. Well, the first thing you need to do is you need to build the nucleus. So once we have the nucleus built, then it's a matter of arranging sufficient number of electrons around that nucleus according to the quantum mechanical model that will allow us to now have a nice, balanced, neutral, electrically neutral atom. So let's go to the Elmo and see what this might entail. So here I am over at the Elmo. So imagine that I start off with, again, the building blocks of atoms, which are protons, neutrons, and electrons. And the simplest way I can do this is start off by putting a single positive charge, like a proton, and putting a single electron into the first energy level, so to speak. So here I have a very simple atom, one proton, one electron, and they basically electrically balance each other out. And as it turns out, this is a viable element. This is basically hydrogen. This is the simplest of all the atoms that we can have, and it belongs to the element that we call hydrogen. Once we have this, how do we go about and proceed to the next element, to the next bigger atom? Well, the next one I can now, what if I now put two protons together? In this case, I can now balance this out with two electrons. That would then give me my second element. This is now going to be helium. So basically, by increasing the number of protons in the nucleus, I can now differentiate between one and two here between these two different elements. You can imagine taking this the next step and now putting three protons in the middle and then surrounding it with three electrons. The only problem is if I put two electrons in the first energy level, they're now getting kind of crowded in there. The next electron now has to go into the next energy level. So this would be our next element, which is going to be lithium. So that looks pretty good so far. That seems reasonable. Does anybody see any problem with this? Well, as it turns out, if you look very carefully, there's two things wrong with this. First of all, remember that the protons tend to repel each other. So if I just leave them like this, they're not going to hold and stay basically viable for very long. The proton will push apart and the atom will basically break apart. So that's one problem. The other problem, of course, is that I don't have any neutrons. So what do I do? Well, as it turns out, the neutron will solve both problems. By putting neutrons into the nucleus, you can now stabilize the nucleus. So what you find is this. In the case of helium, for example, with the two protons there, what I would need is I would need to put in okay, a set of neutrons. So here I have 2 protons over here. What I really want to do is I want to go ahead and put in 2 neutrons to kind of glue the nucleus together. So when that happens, I can now balance this out with 2 electrons. This would then be the proper, okay, atom for helium. So this is now my helium. And in general, as a rule of thumb, what you find is that you need a number of neutrons that is going to be equal to or greater than the number of protons that you have. Okay, so in this case, I have 2 protons, I'll need at least 2 neutrons. If I have 3 protons, I'll need at least 3 neutrons in order for me to hold it together and basically make it stable. And the more protons I have, the more neutron I'm going to need, because as it gets bigger and bigger, the nuclear strong force gets weaker and weaker. So each neutron, in addition, will not serve as much of a glue than before. And so basically, to distinguish between different elements, what we do is we count up the number of protons. The number of protons basically dictates the identity of a particular element. So hydrogen will always have 1 proton, okay? Helium will have 2 protons, lithium will have 3 protons, and so on and so forth, okay? Now we notice that these guys will need neutrons, especially for 2 protons and up. But in the case of hydrogen, we have only 1 proton. So the question is, do we need a neutron for the hydrogen? Of course, the answer is no. We don't need a proton for the we don't need a neutron for the hydrogen. But the question then becomes, can we have one? Can we have a neutron? And as it turns out, we can. So this is what it would look like. So let's go ahead and take a look at hydrogen again in more detail. Imagine for hydrogen, I can have a single proton over here with a single electron. This will then be my hydrogen. Okay, but I can also have a situation where I have a proton over here, and I can actually pair it up with a neutron. Okay, sorry, a neutron. And what that does is that would then allow me, to still, have a single electron here, and this will still be hydrogen. As a matter of fact, I could actually have another situation where I have a single proton here, and I can have 2 neutrons stuck to it, and that'll be perfectly okay as well. As long as I don't change the number of protons, I still have hydrogen as my element. So what is the difference between these 3 different forms of hydrogen? Well, we need to come up with a brand new term to describe this kind of situation. So let's go back to the slideshow and see what happens. In this case, in building an atom, we can now create what is known as the fact that atoms are composed of 3 fundamental particles: the electron, the proton, and the neutron. And if all atoms are made out of the same particles, then why do different atoms exhibit different chemical properties, their ability to combine with atoms of different elements? Well, what happens is that, in this case, since the atomic volume is determined mostly by the space within which the electrons move, there's a lot of space between the electrons and the protons. What happens is when atoms interact with each other, it is really the outermost electrons that are intermingling. So we kind of saw that in our last think tank question, where it was the electrons that are repelling each other that make things feel like they are solid. Well, in terms of interactions between atoms, guess what? It is those outer electrons that are going to interact with each other. And furthermore, it is the number and arrangement of the electrons that affect the way an atom can interact with other atoms. And this now kind of goes into the discussion of chemistry that we're going to pick up a little bit later on. But before we do so, let's again remind ourselves what happens when we look back into the nucleus. Remember that if we have a different number of neutrons attaching themselves to a particular number of protons, then we have a situation where we can have the same element, but the atom look a little bit different because of the differences in number of neutrons. In this case, we're going to define something called the isotope. And isotopes are nothing more than atoms with the same number of protons, but different number of neutrons in the nucleus, like the case that we had for hydrogen. You could have hydrogen that has a single proton. You can have hydrogen that has 1 proton and 1 neutron. You can also have hydrogen that has 1 proton and 2 neutrons. They are all different isotopes compared to the others. So that's what we mean by isotopes. And to keep track of these isotopes, the 2 things that we're going to keep track of is 1, the atomic number. We use the letter Z to represent this. This is just counting the number of protons that is in the nucleus. So for the case of hydrogen, its atomic number is always going to be 1. There's always going to be just 1 single proton in the hydrogen, so Z is always 1 for hydrogen. And then, of course, for helium, Z is going to be 2. Lithium, Z is going to be 3, and so on and so forth. Now, aside from the atomic number, we also need to keep track of something else. We also need to keep track of something called a mass number, and we use the capital letter A for this. This is now the sum of the number of protons and neutrons in the nucleus. The reason why this is called a mass number is because we recall the majority of the mass of the atom actually resides in the nucleus. It is determined by the proton and the neutron. They are about the same mass. Okay, electron has very, very little mass compared to them. Okay, only about 2,000 as much mass. So the whole idea is that the mass is determined mostly by protons and neutrons. So if I have only a single proton, you can imagine that to be a mass of 1. If I have a proton and a neutron, all of a sudden now you're kind of doubling the mass of your atom. Okay, and so the mass number counts up the number of protons and neutrons in the nucleus. So we can use this two information to kind of distinguish one isotope from another. So one we can call hydrogen 1, for example, where it has a mass of 1. So the atomic number is 1, the mass is 1. Okay? If I look at the second isotope now, where you have 2, okay, 1 proton, 1 neutron in the nucleus, 2 particles in the nucleus, then this is now going to have an atomic number of 1. Okay, Z is 1, but now A, the mass number is going to be 2. So we usually call this hydrogen 2. Okay, there's also a very special name that we can give it. It's called deuterium, for example. Some of you may have heard of this. Okay? And of course, the third variation is now you have 3 particles in the nucleus. Okay, the Z number is still 1, but now the A number, the mass number, is now 3. Okay, 1 proton, 2 neutrons. In this case, okay, we'll call this hydrogen 3. Another name for it is tritium. Some of you may have remembered this from the movie Spider-Man 2, where the villain Doc Ock was actually looking for an energy source composed of tritium. And I actually have some things here that kind of show you what these things might look like. As it turns out, in nature, most of the hydrogen that we see in the universe are of the first type, hydrogen 1. As a matter of fact, about 99.985% of all the hydrogen is of this type. But there is a small percentage, 0.015%, is going to be of the second type, hydrogen 2 or deuterium. And guess what? Even in a sample of water, for example, there is a mixture of hydrogen 1 and hydrogen 2. So water, remember, is H2O, 2 hydrogen to 1 oxygen. Okay? Most of us already know this. So that means that in the hydrogen that is in the water, 99.985% is going to be regular hydrogen 1, but there is a small 0.015% will be hydrogen 2. And interestingly enough, during World War II, American spies discovered that the Nazis were actually taking seawater and isolating the water that had the hydrogen 2 or the deuterium in it. They were creating what we call, and processing heavy water. And well, there's only one reason for that. They were trying to make an atomic bomb. So with that, there was a push in basically for our own development of a hydrogen atomic weapon, and that's where the atomic bomb was actually created when the Manhattan Project was recommended. Well, here is a sample that basically is deuterium water. In this case, all the hydrogen in this sample of water is not your regular old hydrogen 1, but rather it is deuterium. And so interestingly enough, when you look at the two samples, they have the same volume, 18 milliliters. And yet this has a mass of 18 grams, while this has a mass of 20 grams. It is heavier and more massive than the regular water because of the fact that the hydrogen in here is twice as massive as the regular hydrogen that is in the regular water sample. So if you take this deuterium water and you freeze it into a chunk of ice, you put it into regular water, it will actually sink in regular water because of its greater mass per unit volume, greater density. But of course, I don't want to do that because this was actually pretty expensive, so I didn't want to kind of waste this. There's also the presence of tritium. Tritium, as it turns out, is not found naturally, but you can actually create it in the laboratory. And there was actually funding for it, doing some research, and they have actually developed a method of creating tritium gas in the laboratory. This was actually done for the militaries where they wanted to replace the radium paint that they were using for their glow-in-the-dark watches for nighttime operations. They found out that the radium paint actually was kind of dangerous because of the radioactivity, can actually cause skin cancer. So what they want to do, they want to have something safer to replace that glow-in-the-dark diode. And this is what they came up with. In here, in this plastic capsule, is a glass tube that is coated with a phosphorescent material. And inside the glass tube is injected tritium gas. Now, the tritium gas is a radioactive material. That means over time, it's going to break down and give off very high energy electrons. Now, the glass tube is coated with a phosphorescent material. So when the electron hits it, it will give off a flash of light. So basically what this is that it is a light source that doesn't have any external energy sources. So what they did was they sealed off two ends of the tube after injecting the tritium and sealed it with high energy lasers and encapsulated it like this. So inside there's this radioactivity that's going on all the time, and the electrons are bombarding the tube, and what it does, it gives off light. So in total darkness, you can actually see this light source from about 200 yards away. and it will last for over 50 years without any kind of battery or energy source from the outside because of this radioactive decay of tritium gas, okay, hydrogen gas. And it turns out, it is relatively benign because of the encapsulation. The electrons don't really get through, and it's not a dangerous radiation source. So that's the idea behind isotopes, okay? Same number of protons, but different number of neutrons. They are the elements, atoms of the same element, just a little bit heavier, okay, and so on, difference in mass. And every element known to us have, at least one isotope. Most of them are radioactive, they don't hang around for very long. Others are a little bit more stable, okay? All right, let's take a look at what else we can kind of define in terms of some basic definitions. So by definition, we can talk about the following now in terms of making atoms. Okay, we can define something called elements. The element is nothing more than a substance that is made up of atoms with the same atomic number. Okay, so that's how we organize the building blocks of matter. It's kind of like looking at the English language. You look at how the English language is structured. Okay, of all the languages here, basically everything in the English language is based upon a set of 26 characters in the alphabet. And so by putting those characters, those letters into different combinations, we can form words. By putting words together, we can form sentences. Putting sentences together, we can form paragraphs that would then lead into novels and so on and so forth. So everything builds from that particular set of 26 letters, and the complexity kind of grows from there. In the same way, there's a certain number of different atoms that can be grouped together to form these different elements. Those elements are kind of like now the letters of the alphabet. By putting the elements in different combinations, we can now form more complex material that will basically make up all the things that we see around us. So the idea of the elements kind of like the letters of the alphabet for matter. And furthermore, depending on how the atoms are arranged into a macroscopic structure, we have something called allotropes that are possible. Allotropes are nothing more than different forms of a given element that is distinguished by differences in physical structure. It has to do with how the atoms of a particular element are arranged together to form a macroscopic structure. So you can have the atoms stacked on top of each other directly, or you can have them shifted off a little bit onto the side. And so depending on how they are arranged, you can have different physical and chemical properties. So in this case, for example, if you look at this particular material, this looks kind of yucky looking. I'm holding it with a piece of paper because it's very crumbly, so if I touch it, it will basically get on my hand and leave a black mark. So this is actually coal, very similar to another material called graphite, that has similar properties. Very easy to crumble this. This is actually made out of the element carbon. And so this is one form of carbon, that has certain properties. It crumbles very easily, and that's why when you look at pencil, for example, the pencil lead is not the element lead, but rather it is graphite. It is a form of carbon that is very brittle. It breaks apart very easily. So when you press it against a white sheet of paper, it leaves a black trail as it breaks apart behind it. On the other hand, if you look at a different material, here I have a very small material, so let's look at it under the Elmo. If you take those carbon atoms and arrange them in a slightly different manner, you can now get something like this. This is actually a small diamond. Now I couldn't bring a large diamond because they're pretty expensive, but I think this will do. So as you look at this, for example, you'll be able to see, where is it? Oh, there it is, that little chip right over there. This is a diamond. You can probably look at your wife's ring or your parents' ring or whatever it might be, and you can see a diamond there. The diamond, as it turns out, is also carbon. And in this case, the carbon is arranged in a slightly different fashion, so it has very different physical properties. So let's kind of see what they look like in terms of a model. So I have some models back here. So here is a model of what carbon look like when they're in the graphite form. So in this case, if you look very carefully, notice that each of these black stars represent a carbon atom. And in this case, they are arranged in a hexagonal shape, almost like a honeycomb pattern. But they are arranged so that they are flat as a sheet in 2 dimensions. So notice that this sheet right here, all the atoms are within that sheet. And the sheets then are connected together by very weak connections. So these are very weak bonds, as we call them. So when I try to grab this and slide them across, the sheets slide past each other very, very easily. And that's why graphite would crumble so easily when you apply pressure to it. It will basically break along those planes where the weak connections are. So it is a very soft material. On the other hand, if I arrange the carbon atoms in a slightly different configuration, in one that looks like this now, it has a very different type of structure. In this case, they're still kind of looking like hexagonals, except now it is 3-dimensional. It is not flat. And as you rotate them, you can kind of interlock to each other. And in certain position, you might see other kind of configuration, like a square on one side and so on. And now they're kind of locked up very, very rigidly. So when I try to press down on them, they don't shift very easily. This is now the structure for diamond. One of the hardest substances known to man. Now, when we say hard, we don't mean that it is indestructible. Hard has to do with the fact that it is very difficult to scratch the surface of it. So hardness of a material has to do with its ability to be scratched. So diamond, very difficult to scratch the surface. The only thing you can scratch a diamond with is with another diamond. Whereas graphite, you can scratch it with all kinds of stuff, and it will scratch and basically leave a mark very easily. Okay? And so by arranging the atoms differently, you get different structures. These are called different allotropes of the same element. All right, continuing on, we can also define something called molecules. A molecule is really a collection of atoms that behave as a unit, okay, and it's always electrically neutral. And so water would be an example of a water molecule. It would be an example of a molecule. And we'll get to more to this a little bit later on. We can also define something called compound. This is a substance that is made out of 2 or more elements in the same fixed composition. Now, in this case, the compound is kind of like words that you form using the English language. So when you put, A and D together, those 3 letters, A and D, you form the word and it's always those 3 letters in those forms that will give you the same word over and over again. So compounds are basically 2 or more elements put together in the same way, same proportion all the time. And then we also have, something called an ion. An ion is an atom or group of atoms that has a net charge. So in this case, it is possible for an atom to either lose an electron and become what we call a positively charged ion or a cation, or an atom can actually gain an extra electron or 2 and it becomes a negatively charged ion, an anion. So it is possible for electrons to kind of migrate from one atom to another. So certain atoms can actually lose electrons and become positively charged because they're now lacking some electrons. Others can actually gain the electron and become positively charged. And again, we'll get into more of this a little bit later on. This is just some basic definitions for now. So that means that in order for us to discuss all the different kinds of elements there are, we need to somehow represent them using certain symbols according to the names. So here are some atomic symbols that we can use for some basic elements that we have seen. So for hydrogen, helium, lithium, beryllium, boron, carbon, these are all very common elements that we see around us. The symbol is pretty simple. The symbol usually comprised of 3 letters. The first of which is always capitalized, and then the next 2 is always going to be lowercase. So you can have either 1 letter, 2 letters, or 3 letters, for the symbol. The first one is always capitalized. Be very careful about that. And the second and third is always lowercase. So sometimes it's real easy now to remember because all we're going to do is use the first letter or the first couple of letters to represent a particular element name. So going back to the slide, notice that hydrogen is just H. Now when you get to helium, because we already use H, we now use He for helium. So Li for lithium, Be for beryllium, B for boron, C for carbon, and so on. So it's pretty straightforward. However, there are elements that have some strange looking symbols, and it might look something like this. And the reason for this is because a lot of these elements, while we use a more common term for them nowadays, in the past there have been other names given to the same element. And a lot of these came from the Greek or from Latin. And so they would carry these Latin names, and the symbol would be derived from these Latin names. So going back to the slide, we can see that for copper, for example, it was originally called cuprum, and so Cu for copper. Gold is really interesting. Gold, the original Latin name was aurum, which means shining dawn, to describe the color and the shine of it. And so the Au symbol is used to represent gold. So iron is Fe, lead is Pb, and so on and so forth. Now some of these, with usage, you will become familiar with them. Now of course, you don't have to memorize all this all the time. There is a set of periodic table in the resources of Lau Lima for this course that you can go ahead and download, print it out, and have with you as a reference. So there you will actually have an alphabetical listing where you have the name of the elements, and you can look up this symbol very easily. I also have it arranged according to atomic number. So going from the lowest mass to the highest mass. So with 1 proton to 2 and so on and so forth, as the mass increases, it would go down the table that way. You can use that to also look up the name and look up the atomic symbol for that as well. So once we have the atomic symbol, we can now use the atomic symbol to represent certain elements as well as their isotopes. So let's go to the ELMO and see how this might work for some of the things that we've already talked about. So for example, when we look at hydrogen and their isotopes, we find that there's different things. So we have hydrogen, for example, where I have 1 proton, 1 electron. We have deuterium, we have 1 proton, 1 neutron, and an electron. And then finally, we have 1 proton, 2 neutrons, and 1 electron. So how do I distinguish between these 3? Well, this one now is going to be called hydrogen, but I'm going to use the symbol hydrogen. And what I'm going to use the upper and lower corners of the left-hand side of my symbol. In the lower left-hand corner, I'm going to put the atomic number. So in other words, if I have the symbol like this, I can imagine drawing a box around it. In the lower left-hand corner, I will put the atomic number there, Z. And the upper left-hand corner, I'll put the mass number A there. So for this one, this is atomic number 1, mass of 1. So H11, this is now H1 or hydrogen. This one now, same symbol, still hydrogen, but now only 1 proton, but now I have 2 charges, particles in the middle, so that's the mass of 2. This is now the symbol for deuterium or H2. Here I have H1 proton, so atomic number 1, but now I have 3 mass particles in the nucleus. This is now H3, for the tritium isotope. So I can now use these symbols along with some numbers to represent a very specific isotope for a particular element. So that's how we're going to be using these symbols. And there's going to be other things that we could do with the symbols as well in basically formulating the formulas for different compounds and so on and so forth. But we'll get to more of that when we get to chemistry. All right, so let's take a look at the distribution of what is available to us in terms of elements that we see around us. So first of all, let's take a look at the percent or mass percent distribution for the 10 most abundant element in the Earth's crust, ocean, and the atmosphere. So in our environment, we see that the most abundant element is actually oxygen. Most people would not realize this, but as it turns out, almost half of everything that we see around us is oxygen. And then, of course, we have a second most is going to be silicon. It's about 25%. Now, silicon is a very interesting element that we're going to talk about later on. So do not confuse silicon with silicone. Those are two different materials. So silicon is what we're going to be dealing with. So things like aluminum, iron, calcium, sodium, potassium, those are all very common elements that we see around us. So these are the 10 most abundant. Now, of course, depending on where we look, the percent composition might be a little bit different. So let's take a look at a different location. What if we look at the abundance of elements in the human body? Now we see something very interesting. In this case, again, most people don't realize this. A lot of time when you're asked, what is the most common element in your body, a lot of people will say carbon, because we are after a carbon-based life forms. It turns out, it is still oxygen. Why? Because we're mostly water. Water has a lot of oxygen in it. And remember, this is by mass. Although there are more atoms of hydrogen than oxygen, hydrogen has a very low mass compared to oxygen. So that's why oxygen is a predominant element in our body in terms of mass. And though notice that after oxygen, now it is carbon that is the second most abundant. So unlike the Earth, which has silicon as the second most abundant, we have carbon as the second most abundant element in our body. And then, of course, everything else. And the interesting thing is, of course, we're not worth very much. If we took all the elements in our body and kind of distilled it in terms of how much we have of each, and we were to sell it, as just the minerals that are in us, as elements that are in us, we want to be worth, less than $1. Very, very little worth in that sense. But of course, we are more than the sum of the parts. All right, so that's the mass distribution. And so once we have all these different elements, how do we go about organizing them in a way that we can, again, get some useful information out of them? Well, this leads us now to our next topic of discussion, which is going to be, topic number 2, we're going to discuss now the periodic table, the first part. Now to talk about the periodic table, what I want to do is kind of show you a website. Here, this is a very useful website that, again, you can get the URL off of Laulima. But if you remember, it is very simple. It is webelements.com. And this shows an arrangement of all the elements that we know of nowadays. As it turns out, we know of about roughly 118 elements. So a lot more than the 26 letters of the alphabet. So if 26 letters can allow us to create so many different types of words and so on and so forth, we have tens of thousands of words that we can create using that. Imagine the combinations that are possible now with 118 different building blocks. We can create basically millions upon millions upon millions of different combinations in terms of compounds and material that we can build from this. And we're going to arrange them in a very interesting fashion in this particular way called a periodic table. And so I'm just going to show you the structure right now. So you take a look. Notice that this is really color-coded at this point. And what it is a series of rows and columns that make up this particular chart. Now, of course, you can ask, why don't we just use a regular, simple column format? Well, you can, but the amount of information you get out of it is going to be limited. This is much more useful arranging it this way. So we're going to go back and see what this looks like. Now, if you look very careful, notice again, they are arranged in these rows and in columns. We're going to go ahead and break them down in general. And also notice that, in this case, we can look at some very general breakup, just like in the case of the letters of the alphabet. A very simple way of breaking them up and organizing them would be to separate them into the vowels and the consonants. Very general separation between the two. And then, of course, we can do other things that we can use to categorize them as well. In the same way, we can take the periodic table and separate them into some very simple, basic categories that will allow us to see them very quickly and then do more refined categories later on. So let's take a look at a very simple way of separating these into different things. So by looking at the periodic table, we find that we can classify them by what we call periods. In this case, it started off by a Russian chemist by the name of Dmitry Mendeleev back in the late 1800s. And he first attempted to organize the elements by their increasing in mass. So basically, he put the lightest elements first, and then he slowly put in order elements of increasing mass. But as he was doing this, he noticed something very interesting. He noticed that hydrogen, the first element, the lightest element, has some very interesting properties. It was a gas at room temperature, and if you light a match to it, boom, it blows up. It's very, very reactive, very, very violent. The second element is also a gas, helium. And yet helium, for some strange reason, doesn't react at all. You can light it and try whatever you want with it, but it doesn't react. It doesn't combine with other things to form new material. Whereas hydrogen would combine with a whole bunch of different things to form new material. So very different in characteristics. So he's like, okay, that's pretty good. And then he went to the third element, lithium. Lithium, now as it turns out, is a metal. That's kind of whitish in color. And this metal is very soft. So you can actually cut it with a butter knife, but it has this metallic sheen to it. And if you take this metal, you drop it in water, boom, it blows up in your face. Very, very volatile, very, very quick to react. It kind of reminds you of hydrogen, except that it is a solid rather than a gas. And so what he did was he slowly built up a recognizable pattern. Whereas he went from one element to the next describing the physical and chemical properties, he noticed that there's a repeat in pattern. So when he came to the 11th element, for example, when he came to sodium, he noticed sodium had some very interesting properties. It is a white metal, kind of silverish in color, very soft, you can cut with a butter knife. When you took a chunk of it, drop it in water, boom, it blows up in your face. Very reminiscent of lithium. When he got to the next one, further down the line, he encountered another element, potassium, that was also very soft. You can cut it with a butter knife, drop it in water, boom, blows up in your face. All of a sudden, you began to see these repeating patterns where certain elements had the same physical and chemical properties. And he thought, well, maybe that would be a good way to kind of organize them. And so whenever he saw this, what he did was that he started by putting them across in a row. And when he saw a repeat in pattern, he would basically put the element that had the similar patterns under each other. And then he saw a repeat of this particular series of repeated patterns. And that's where the term periodic table came from the repeating cycles or periodic nature of these characteristics that he saw in the different elements as he arranged them. And so the idea is that he recognized the important fact that similar physical and chemical properties occur periodically. And so each row of the table is called a period corresponding to a full cycle of a particular change in physical and chemical property, that change in trend. And so a general classification is pretty straightforward. What we're going to do, we're going to divide the elements into three types. The first type will be called the metals. The second type will be called the nonmetals. And the third type will be called metalloids or semi-metals. So let's take a look at the periodic table again to see where these things can be found and what they might look like. So here we are back in the periodic table. What you find is that in general, if you look across here, again, this is what we call a period going across here. So right over here, lithium is the one that has the volatile nature, that metal. As you go across here, the characteristic would change until you get to neon, which has very similar property as helium. It is a gas that is very, very unreactive. And then you get now to sodium, all of a sudden repeats the pattern of lithium and so on. So each of these rows is now a period. And in terms of general classification, you notice that this is now going to be divided into some very simple things. The things that are on the left-hand side over here are what we call the metals. And then the periodic table is actually divided along a diagonal like this, right across here. So from boron down to the bottom here, what you find is that if you imagine a staircase that comes down this way on a series of steps, alternating steps like this, it will then divide the metals on the left, the nonmetals on the right, and along this staircase is where the metalloids will be found. So keep that in mind while we discuss these three different types of material. All right, so let's go back to the presentation. So let's take a look at the first type, which is the metals. So for the metals, basically these are generally found, as we said, on the left-hand side of the center, and center of the periodic table. And they make up about 80% of all elements. So predominantly, all the elements that we know of are metallic in nature. They tend to be metals. And metals have certain physical properties. So let's see what some of those properties are. In general, okay, metals will have the following physical properties. They tend to be very shiny and opaque, so you can't see through the metal. So there's no such thing as transparent aluminum, for example. But they tend to be very shiny, reflective, okay, of light, and so on. Okay? They're also very good conductors of heat and electricity. So as it turns out, for metals, they have electrons that are very mobile. Okay? The electrons are very, very easy to detach from the atoms. And so they serve as the intermediaries that carries not only heat, thermal energy, the collision process, but also carries electrical current, the charged particles that's actually migrating. And so we already learned that from the electricity and magnetism section of our discussion. And also, they have other physical properties of malleability. In other words, metals can be hammered into very thin sheet and bent without breaking. Okay? And there are some very classic examples of this. Gold, for example, is notoriously good in being able to roll out into very, very thin sheets and used for decorative purposes. So for a very small amount of gold, you can get a really large sheet and very thin sheet. And just to kind of show you what it might look like, here is an example of what gold looks like when it has been flattened out into a sheet in terms of its malleability. Okay? This sheet of gold in here is about 1 micron in thickness. That is 1/1,000,000th, okay, 1/1,000,000th of a meter, okay? And it is very, very fragile. It is very light because the actual amount of gold is not that much, but it has been pressed out into a very, very thin sheet, okay? And you can use this for gilding purposes and so on. Okay, here's another metal, same kind of idea, okay? Again, pressed out into a sheet that is about 1 micron in thickness, okay? This is palladium, same thing. Also has that ability to be pressed out into a sheet like this. And we all know that copper can be rolled out into sheets and so on and so forth for construction purposes and so on. Okay? So malleability is one property of metal. Another very interesting physical property of metal, okay, is its ductility or ductile. It can be stretched into wires very easily and pulled into very thin strands. So here's an example of the ductility of copper, for example. So this is a coil of copper wire. And you can kind of tell that the wires themselves are extremely thin, very, very small. Okay, without breakage. So you can draw metals into wires like this without breaking it. So that's another very important characteristic of metals themselves. Okay, so those are metals. And then the second type of material that we can talk about are called the nonmetals. And in this case, these are generally found on the right-hand side of the periodic table. Okay, and these include elements in all three phases. Now, while metals tend to be all in solid state or solid phase at room temperature, with the exception of mercury, and a couple that are very close to room temperature, most of them, the majority of them, are going to be in solid form when we see them in room temperature. Not so for the nonmetals. As it turns out, the nonmetals are predominantly in the gas form. There are more nonmetal gases than there are the other things. But they can also be in a liquid form. Bromine, for example, is going to be a liquid at room temperature. And then you can also have solid nonmetals as well, like sulfur, for example. So here is an example of sulfur, that has a solid state at room temperature. So that would be a nonmetal. So what are the properties of nonmetals? Well, they tend to have the following physical properties. They are very poor conductors of heat and electricity, so they do not have very nice loose electrons, in other words. They are also very brittle and will shatter when you hammer them. So notice that in this case, the sulfur is in a powder form. So even when it is in crystal solid form, if you hit it with a hammer, it will shatter and become very, very brittle, very easily breakable. So that's the general consensus for nonmetals. And so the last group now are now the metalloids or the semi-metals. In this case, these are the ones that are found close to the stair-step line of the periodic table. And in this case, they generally include the following: boron, silicon, germanium, arsenic, and so on and so forth. Sometimes it depends on who you talk to, whether you talk to a physicist or whether you talk to a chemist, that they will either include others or leave out some of these as well. But you can see that they're generally on that ladder. And the idea here is that they have basically properties of both metals and nonmetals. And so for metalloids, they display both properties of metals and nonmetals. A very classic example of a nonmetal is this material right over here. This is a chunk of silicon, which is considered a metalloid. So when you look at a chunk of silicon, notice that when you compare it to, let's say, a classical metal like copper, notice they're both very shiny. They have that metallic sheen to it. So you would very easily mistake this for a piece of metal until you feel it in your hand. It is very low in density, very light, for example, for its size. Also, it doesn't feel that cold. It feels actually kind of warm because, as it turns out, it is not a very good conductor of electricity or heat at all. And so it is a very poor conductor in its natural form like this. So this is an example of a nonmetal. And interestingly enough, you don't find a chunk of metalloid like silicon in the earth by itself. most of the time the silicon, okay, is going to be tied up with other elements in forming compounds and so on and so forth. And we'll see what that looks like in just a little while. All right, so that kind of concludes this particular way of dividing up the three. So let's go ahead and summarize and see what it looks like again on the periodic table. Here we are back on the periodic table. So notice in this case, again, the metals tend to be on this side right over here, and most of them are basically solid at room temperature. And the non-metals are now in this corner right over here, in the upper right-hand corner. And then right along this line, right on this diagonal, that's where the metalloids would tend to be. Okay, metalloids tend to be. So notice at this point, you actually cross over from non-metal through to the metalloids down to metals as you come down this way. Okay, so the next thing we're going to do is we're going to kind of classify them now and group them into groups that are found in these columns. So you notice that these columns are actually labeled, labeled from column number 1 all the way down to column number 18. So it's a very simple way of labeling these columns, just numbering them down this way. So what I want to do now is kind of go through them each at a time to kind of point out some significant properties and characteristics of some of these groupings. Okay, so we're going to go ahead and move on to our last topic for this discussion for the day. So let's move on to the last topic. And this last topic is now going to be the periodic table continuation, part 2. So now that we have classified them very simply using those 3 different types, let's go ahead and do a little bit more detailed classification. So this is what it might look like. So in this case, what we're going to do is we're going to classify by atomic groups. Okay? And the groups are families of elements that lie in the same vertical column on the periodic table. This is very useful because now we can now group together elements that will have similar behavior, so that we can now use it to understand whether or not a particular element will react based on whether a member of its family will react with something. So we can now use that to kind of predict the way that a particular element might behave when it tries to react with other elements to form compounds and so on and so forth. Okay? And so elements in the same group will exhibit similar chemical properties basically. And the groups are often referred to by numbers from left to right across the periodic table or by special names. So let's go ahead and look at them one at a time. In group number 1, this is the first column on the left. These are usually called the alkali metals. Okay? And except for hydrogen, elements of this group are soft, low-density, shiny metals. Okay? As we said before, they can be cut by a butter knife. Okay? They're highly reactive with water and are not found as free elements in nature. These guys are extremely volatile, so when you try to combine them with water or anything else, they will combine very, very readily to form compounds. Okay? Sodium, for example, is a member of the alkali metal. And if you try to bring it in the presence of, let's say, chlorine gas, for example, it will react very violently to form a compound called sodium chloride, or common salt to us, table salt. Okay? So they will form very, very violently compounds through reactions. And again, you don't find them as simple elements. Okay? You have to kind of separate them through chemical process in order for you to have element forms of these. And of course, you probably don't want to do that because they are extremely unstable, so very dangerous to store. If you don't store them properly, you have an explosion on your hand. So keep that in mind. So again, further for the alkali metals, hydrogen is in this group in that it is unique in that it is not an alkali metal, but it is placed in group 1 due to its electronic configuration. It has the same electronic configuration, having one single electron in one of the s orbitals, as we'll see a little bit later on in terms of when we combine our knowledge of the quantum mechanical model with the periodic tables organization. But the idea is that it also has similar physical and chemical properties. If you take hydrogen and you basically cool it down until you can liquefy it, so you bring it down to a very, very low temperature, it becomes a liquid. Once it liquefies, it will now behave like a liquid metal, kind of like mercury, for example. It will have a metallic sheen to it. It will conduct electricity just like a metal would. Okay, so that's why hydrogen is there. Very unique in that sense. And also what you find is that, the reason why these are called alkali metals is that elements of this group are found in ashes that produce a slippery solution when mixed with water. And this is very useful in removing grease. So you use this for basically making soaps. And so this solution is described as being alkaline in the Middle Ages. And this is actually derived from the Arab word, alkali for ashes. And so a lot of time what you find is that elements in this particular family can be found in compounds that are used for making soap. So potash, for example, contains potassium. That is a main ingredient for soap for a very long time we used to make soap. Okay, let's go on to the next group. In group 2 now, one group over to the right of the first group are called the alkaline earth metals. These are very similar to group 1 elements. They tend to be very soft, reactive metals, but not as reactive as group 1. So these guys, if you drop it in water, they won't explode on you, but if you light it with a match, it will burn very, very, very rapidly, okay? And so they form compounds that are alkaline in water as well, okay? But the interesting thing is that minerals, okay, formed from elements of this group have very high fire-resistant properties. So to the alchemists of the Middle Ages, they were known as earth elements, and hence the term, alkaline earth metals, okay? So you have compounds that contain things like calcium, for example. Okay, if you try to burn it, it resists fire very, very nicely, okay? Resists burning. All right, so that brings us now to the third group, okay, group 3 to 12, as it turns out, okay. This is now the block in the middle of the periodic table. These are called the transition metals, okay. They do not form alkaline solutions with water. Okay, they are harder than group 1 and 2 elements and less reactive in water. And also they include some of the most important elements that are used in our society in building the infrastructure for our society, okay. So what are some of these? Well, if you take a look, okay, these are some very recognizable material in there. For example, iron, copper, gold, silver, all fall into this particular category of transition metal. So let's take a look at some of these, okay, on the elbow to see if you recognize what some of these might look like. So here we are at the elbow, okay, so let's take this away. And so basically here I have 4 different samples that I want you to take a look at. And what you find is that, okay, these might look familiar to you because you might have seen them before in one of our previous labs. In this case, we have here copper, has a very distinctive color, okay, and this is zinc right over here. This is nickel, and this is aluminum. And most of the time when you look for these metals, you don't find them again as pure elements in nature. They're usually combined with something else, and you have to purify them. And then of course there are also other things like gold, for example. Gold, as it turns out, is one of those, okay, that will actually, let's kind of zoom in on this a little bit, that can actually be found as, okay, an element, okay, in nature. This is actually gold dust from San Francisco. So during the gold rush, this is what they were looking for. Okay, this is gold dust. Okay, and this is one of the few elements that can be found as, okay, a pure element in nature. Silver is another one. Copper is another one. Otherwise, most of the transition metal will be found as compounds. Okay, you have to purify them. Some other very interesting one is this one over here. This is called, okay, bismuth. And it is right next to lead on the periodic table. The reason why this is very important, it has all the properties of lead, very, very dense, very soft. It melts at very low temperature. You can actually melt this over your stove. But what is interesting is that, okay, this is now being used very widely to replace lead in a lot of different, okay, situations. Lead, as it turns out, is very dangerous for us. So it is poisonous to us. So when we use lead for buckshots and things like that, where there's a chance of contamination in our food, then that's going to be very, very dangerous. So this is now being used to actually replace a lot of the lead that we use in our, okay, society. Okay. Here's another one that's very interesting. This is one of the transition metals. This is titanium. And titanium is kind of interesting because along with a couple of other elements, it has the, okay, ability to resist corrosion. So you've got to zoom in on this, okay? And basically, it is also very light in terms of density, very low in density, and also very, very strong. So these are actually useful in a very, okay, corrosive environment like the human body. So these are used as orthopedic pins, for example, okay, for orthopedic surgery to basically, strengthen bones and so on and so forth until they heal. So these are actually pieces that were used, okay, during surgery that I was able to acquire, and these would cost you about $400 if you were to, okay, use it in surgery for that purpose. Okay, so these are very useful material that you see all around us, and they all belong to the transition metal group. Okay, right in the middle block of the periodic table. All right, so let's kind of move on. So as we move over to the next column, we now are looking at group number 13 and 14. These are now the, okay, elements including aluminum and silicon. Okay, the third and the second most abundant element of the Earth's crust. And except for carbon, none of the elements in these two groups occur naturally in the elemental state as well. So again, that idea, not too many of these elements. So if you recall, we said that about 118 elements are available to us. But as it turns out, most of them that we see, there's only about a dozen that we see, okay, in any common amount. Okay? Most of them are very, very small trace amounts that we see. And even then, most of them are not found in the elemental state. Most of them are found combined with something else in the form of compounds. Only a few elements can be found as pure. Okay, gold, silver, copper, carbon, and so on and so forth. Okay. So in this case, let's kind of take a look at one of the members here. Remember we talked about the idea of silicon? Well, in this case, you don't find this in nature. So what you have to do is you have to grow this particular material in the laboratory. Okay, and you grow them in the laboratory by taking this material. This is, okay, a quartz crystal, and this is silicon dioxide. Silicon and oxygen combine together to form a very specific compound. This is the, okay, basically the one of the most abundant minerals that you can find in the Earth's crust, as we talk about later on in mineralogy. But the idea is that if you can remove the oxygen from here, somehow chemically, you end up with this material. And usually grow this in the laboratory in big boules. And boule is kind of like a large fat bat. And what they do is they take that bat and they slice it into very thin wafers. And one of those wafers may look something like this, okay? It looks something like this. So if you look at it under the Elmo, that's what it looks like. Very nice and shiny like this, so you would think that it is a metal. But if you try to bend it, what you'll find is that you'll be disappointed because it actually will shatter into small pieces like this. I made the mistake of passing this around in my class, and my students were playing around with it, and it shattered, okay, because they were flexing it a little bit too much. Because it is not a metal. It doesn't have the property of metals, okay? Now, what do you do with this? Well, this is very important because you can take that now, and you can etch on it something like this. This is now a silicon wafer that has electronic circuits etched onto it. This is what goes into your computer chips, the processing chip that controls your computer, your microwave, your cars, and so on and so forth. Each of these little squares can go into one of those processing chips. Okay? So that one was a defective one that I was able to get a hold of. Each of those squares can actually be cut out now to form a microprocessor. And so now silicon is becoming very important for us because of the computer industry and so on and so forth. Okay? So that's the use for silicon, very important. All right, let's move on to the next group. Okay, the next group is now group number 15, the nitrogen group. In this group, the elements are all, will all react with hydrogen to produce compound with 3 hydrogen atoms per molecule. And interestingly enough, we can't really group them together because this is the part of the periodic table where the non-metal will then transition into metals further down. Okay, so not all of them will have all the same properties. So you have to be careful. Within this same column, there's going to be metals, non-metals, and so on and so forth. But nitrogen, as it turns out, has this ability to combine with hydrogen to form this particular combination. Also, nitrogen is an important element in this group as it makes up about 78% of our atmosphere. So most of the gas that we find in the atmosphere is nitrogen, not so much oxygen. Oxygen only accounts for about 20%. Okay, so very important to see this. Now, when we move to the next group, group number 16, for example, these are now called chalcogens. Okay, and interestingly enough, the elements in this group are often referred to as the ore-forming elements. And so oxygen and sulfur are commonly found in metallic ores. So when we talk about ore-forming elements or the chalcogens, we're really talking about mostly oxygen and sulfur. Now, why do we call them that? Because as we said before, a lot of the transition metals that we find in the Earth's crust are not found as pure elements. They are found as compounds that have been who have the metal combined with either oxygen or sulfur. Okay, those are the ores that we look for. So for example, when we want to find iron, we want to get iron, this is what we look for. This is a particular type of iron ore. This is called hematite. This is iron and oxygen combined together. So by extracting the oxygen, we can then end up with pure iron afterwards. So this is a very important ore of iron. Another very interesting ore of iron is this one right over here. This one's kind of interesting. You look very carefully, it has a very nice, shiny, gold color to it, yellow color to it. And when people first found this, they thought, oh, wow, I struck it rich. Okay? They thought they had found gold. Well, as it turns out, guess what? This is called fool's gold or iron pyrite. Okay? The color is actually come from the combination of iron with sulfur, with sulfur, that yellow color. And it's kind of funny because when you look at some old Western, you can see, an old timer, who is a gold prospector, comes into the saloon and drop down a gold nugget and ask for a shot of whiskey. What would the bartender do? The first thing he would do is to pick up that piece of gold and bite down on it. Okay? The reason for that is because gold is very, very soft. Okay? And gold is very malleable. Okay? So by biting down on it, you can actually dent it. You can actually bite into it. You bite down on a chunk of pyrite, iron pyrite, you chip your tooth if you bite too hard. So very different. So that's how they distinguish between iron pyrite and gold. Okay? You can also have other things like this. This is, for example, galena. This is lead sulfide. So this is lead along with sulfur in here. And you can actually feel, if you had an opportunity, how dense this is. So during one of the labs, you actually get to experience what this feels like when you feel some galena or, in this case, lead sulfide. So the idea is that in this particular group, you can actually find a lot of ores that are made from something combined with this particular member of this group, oxygen or sulfur. As we said before, most of the time you don't find them, the metals in nature as free elements. All right, so the idea is that, we have now looked at these different groups. Let's go to the next one. Group number 17 are now called the halogens. This is a group that will have elements that are highly reactive nonmetals, okay? And these elements in this group are often referred to as the salt-forming elements. The reason for that is because these are the guys that will now combine with the alkaline metals and the alkaline earth metals to form salts. Sodium with chlorine, sodium chloride. Potassium and fluorine to form potassium fluoride, and so on and so forth. Okay? Very, very important group of elements as well. Very, very reactive. Then the next group, group number 18, are now called the noble gases. These groups are usually colorless monatomic gases. That means gases that are made out of single atoms of the element, okay, at room temperature. And these elements were once thought to be inert. That means they do not combine with anything else. However, since the 1962 or so, many compounds of krypton, xenon, and radon have been discovered. Okay, so for example, xenon can basically combine with fluorine, for example, to form xenon tetrafluoride, a very exotic material, and so on. But overall, as far as we're concerned, okay, we can imagine them to be inert, that they do not react whatsoever. Okay, so keep that in mind. And then there are two others that are kind of a little bit out of the way in terms of being grouped together. These are not in a column, but rather they're in a row at the bottom of the periodic table. These are called the lanthanides. They're element 58 to 71. Okay, and elements of this group have very similar properties and are often found mixed together in nature. They're very difficult to separate. Okay, but nowadays we want to separate them because they were found used in a variety of different applications. For example, fabrication of LEDs for laptop computers, okay, lasers, okay, high-strength magnets, as well as glass coloring agents, and so on and so forth. One particular element, neodymium, for example, okay, have been combined with boron and iron to form very, very strong neodymium magnets that basically serve as the magnetic reading device for your hard disk drives. They will be basically providing the magnetic field that allow you to encode and decode information on your disk drives. Okay? The last group that we're interested in, okay, are elements from 90 to 103. These are called the actinides, okay? And this element group also have very similar properties and are extremely difficult to purify. However, okay, two of them are important. Uranium and plutonium, for example, needs to be purified for use in nuclear power plants to supply nuclear energy. Elements that are greater than Z equal to 92, in other words, with 92 greater than 92 protons, okay, are called the transuranium elements, and they are not found in nature. So any of the heavier elements, okay, above uranium are actually man-made in the laboratory, and we usually, when we only make a few atoms of them to prove their existence. Okay, so most of these do not exist in nature as natural. Okay, so let's go ahead and summarize some of the things that we did today. So in review, we find that we're looking at building atoms that make up matter. We looked at the periodic table in terms of classifications in groups and periods. Okay. All right, so for the next time, think about the following. For the think tank, okay, what makes a gold atom different from a lead atom? How are they alike? Okay, during the Middle Ages, alchemists attempted to change lead into gold. And the question then is this possible? And basically explain why or why not. Okay, so from now until the next session, okay, continue thinking about this. This is Roger signing off saying, think physics.